Good morning or good afternoon, everybody. This is John Levine with Levine Electronics and Electric. Welcome to another exciting presentation by one of my favorite speakers, Terry Smith of GE Multilin. If you have a question, you can put it into the chat. Just type it in and I'll see it, and we'll try and answer it sometime during the presentation. With that, Terry, I'll let you get rolling.
All right. Thank you, John. Thank you for having me today. And thank you guys for attending in this weird way that we're interacting with each other nowadays. These questions and asking questions in John's question panel are of paramount importance. So please feel free to ask your questions, right? And we'll address them. And with that said, also to keep you engaged, John figured out this way to do these poll questions. And so from time to time, we'll have poll questions inside this presentation. And as we talk about transformers, and I'm going to spend most of my time today talking about transformer differential protection. We'll cover some of the settings, how you wire it, and we'll also talk about how transformer differential protection works and why it's sort of unique in the differential world, and because we have to do several different types of compensation because it's a transformer. So with that said, I mentioned that John likes to do these polls, and so he makes me come up with poll questions. So I always like to find an interesting poll question. That's the first poll question to keep you guys awake and let you figure out how to do these polls. So the first poll question is, who was the better, since we're talking about transformers, who was the better actor or lead actor in a Transformer movie? Was it Marky Mark or Shia LaBeouf? So the poll's open. I'm anxious to see your responses. Might be the most important poll we do. Nobody's voting. Maybe I should have put a third option on there of what are you talking about?
Needed Arnold Schwarzenegger.
Yeah. Well, he wasn't in those Transformer movies, was he?
Oh, you're right. I'm thinking Terminator.
Terminator.
Yeah.
That was a different thing altogether, John.
Got it.
Okay, we got a lot of Shia LaBeouf fans today because they're saying 62%. That's amazing. I thought Marky Mark would certainly surpass Shia LaBeouf. So, John, if you want to close the poll, and we'll proceed with my presentation and the real stuff here.
Okay. You got the screen.
It is showing that the audience view. Let's see. Show screen.
They can see it. They should be able to see it. I see it.
Okay. So let's proceed on. So transformers, by and large, they're important because they are a large, expensive device. Now, the transformer that you see here, this transformer's got a conservator tank. That looks like a transformer that's around, 50, 60 MVA. So a transformer of that size, if we're going to buy one of those things, and we're going to buy it from a normal manufacturer, we would typically buy that. We've probably got a lead time of around a year. So when I last bought transformers, which is 12 years ago or so now, that's what we had as a lead time, somewhere between 9 months and a year. And they were expensive. So we want to protect them, and things that we protect that are expensive, we really want to trip fast and limit the damage on, and so that's why we use transformer differential. Now, I broadly categorize power transformers, a lot of power transformers, into 3 broad categories, and really I should say 4 broad categories. There's generator step-up transformers, like the one you see here. And the generator step-up transformer, it has 2 real jobs. And its first job is to transform the voltage that we generate at from around 13 kV up to a high voltage transmission level so that we can transmit the power at a lower current. The other job that a generator transformer performs is it typically has a delta to Y conversion. And that delta conversion, or the delta connected windings, are typically wired to the generator side of the GSU rather than the high voltage transmission side. So what that does for us is that blocks the zero sequence current from the generator. So if we have a ground fault out on that transmission line from something like a big blue herring or some other large bird that can span the conductor, or not the conductor, but the insulator, and can cause a phased ground fault, that that transformer will block that zero sequence current, and we won't see that on the generator, which means we don't have to coordinate with the ground elements out on the transmission system. It also means that we're protecting our generators from those zero sequence currents. We will still see the negative sequence current, but not the zero sequence. Another broad category that we have is a step-down transformer. So a step-down transformer is a transformer that we typically have at the other end of the transmission line. So this might be in an industrial facility. It could be at a distribution utility at their substation where they transform from high voltage that we're transmissioning to medium voltage distribution. So this is something in the neighborhood of like 161, 230, 500 kV down to a X winding or a lower voltage winding of 12.47 kV or 25 kV, something in the neighborhood, some medium voltage. It does two things for us as well. It transforms that voltage so that we don't have to have some sort of a massive transformer outside our home to get down to 120 in our home. But then the other thing it does for us is that the distribution system is subject to a lot more ground faults than the transmission system because the insulators are smaller. Their insulators are for 12 kV versus 230 kV. So a blue herring has the wingspan to span across an insulator at 230 kV, but a squirrel can span across a 12.47 kV insulator. So squirrels can cause lots of ground faults. So what that does for us is that the delta side of the step-down transformer is wired on high voltage side of the transformer, the transmission side. And the Y connection is wired on the distribution side at 12.47 or the medium voltage level. So that Y connection typically on both of these, it's step down in the GSU, is typically grounded either solidly or impedance grounded in some way, and that gives us enough ground fault current that we can sense the ground faults and we can coordinate with it. But also it'll block in the step down, just like it blocks the zero sequence currents from the generating station. It'll block the zero sequence currents from the transmission system. So I don't need to coordinate my ground protection for my transmission system with the ground protection out on the distribution system and worry about false tripping my transmission system for every single squirrel out there that we're going to electrocute. Another broad category is an auto transformer. Auto transformers, they don't have to just be the thing that I think about, but when I think about them, I think about an auto transformer as something that steps down from EHV, extra high voltage, to high voltage in a utility switch yard. So this would be something that goes from 500 kV to 230 kV, or 745 kV to 230 kV, and it's wired as you see here. Now, as you see this one, the auto transformer a different thing in that it's just got one real winding. It does sort of have a high voltage and a low voltage winding, but there's no phase shift associated with it. And we don't block any zero sequence currents with this like we do the other guys. And I mentioned that it doesn't have to be like what I think of it, because you also find these sort of transformers, these auto transformers and things like drive, voltage regulators out on the distribution system, a lot of different things. The other place that we find transformers, I said there was a fourth location. The other place that we find transformers is inside of industrial facilities. You know, as we get down into the industrial facility, we might step down from medium voltage from 4 kV down to 120 kV, that sort of thing. Now, when we get down in that level, typically we don't have transformer differential. Usually when we're talking about transformer differential, which we'll spend most of our time on today, we're talking about one of these first three types that I mentioned, these bigger, larger transformers. Okay. So if we're going to talk about transformer differential, let's talk about what transformer differential is. So differential, basically, it doesn't matter if it's transformer differential, motor stator differential, generator stator differential, or even a bus differential, for that matter, a line differential. Differentials all work by the same principle. We're going to measure the current into the zone of protection, and we're going to measure the current out of the zone of protection. Those two currents should vectorially sum to zero. If they don't, we have a fault. So, for example, you know, if I look at this system here, let's see, let me get my pen. Oh, pen. So I've got current flowing here. So that looks like current flowing into the zone of protection. That looks like, let's say that's 10 per, or 1 per unit, if it's under normal load conditions, 1 per unit at 0 degrees. And I've got current flowing here, right? So that's current leaving the zone of protection. That looks like 1 per unit at 180 degrees. So those two vectorially sum to 0 at whatever angle you want to, because it's 0. You know, if I have a fault here, you know, I could have current flowing here to ground, right, or to between the phases. And I could have it flowing here, right? Now, if that's the case, then I'm in this situation here, right? So I've got current flowing into the zone of protection. So that looks like current on the left flowing into the zone of protection. That's 10 at 0 degrees. Current on the right flowing into the zone of protection. That's 10 at 0 degrees. That's 20 at 0 degrees. So that is differential current that looks like a fault. You know, if I don't have a source out here, then I don't have this current, right? So this current I'm Xing out right here. And if that's the case, I've got 10 at 0 degrees on this side, right? 0 on the other side. So 10 at 0 and 0 at 0, when I vectorially sum those, that's 10 at 0. That's differential current. That would cause me to operate. So, at its basic core, that's what differential is, and that's how differential works. The big challenge around differential, though, around all differential, is how do I account for CT performance errors, right? So what if I have a differential? The challenge is never really to get it to operate for a fault. If it's set right, it operates for a fault. The real challenge around differential is preventing it from misoperating when you have a through fault, a fault outside of the zone of protection. So that's true of all differential. And the real reason that's a challenge is because CTs aren't perfect things. So the current transformers that we're using to measure this current and present that current to our relay is not a perfect thing. So let's go back and imagine for a second. Let me go backwards in time. Backwards is never a good direction to go, but we're going to go that way. And let's grab an eraser and erase some of this junk off of here so it's a little bit clearer. And let's assume now that, let me get this off of here. So let me get my pen back. So let's assume that I've got a fault right there, right? If I've got a fault right there, that looks like 10 per unit of current 0 here, and that looks like 10 per unit at 180 degrees there, right? But what about these CTs? If these CTs are imperfect, this might look more like, I don't know, 10 per unit at 0 degrees, right? Because maybe that CT does perform perfectly, but this other CT over here performs less than perfect. So over here, this looks like, instead of 10 per unit at 0 degrees, it looks like 6 per unit at 180. So we have 6 per unit at 0 degrees, or excuse me, 6 per unit at 180 and 10 at 0. That vectorially sums to 4 per unit. Now that's differential current. That caused me to operate unless I do something to take care of that. Now the way that we take care of that in most differential schemes is we use something called a slope differential characteristic. And that's what I show here. Now on this slope differential characteristic, along this axis is a restraint current, and along this axis is a differential current. And then this blue line that I show there, that blue line is the operate characteristic. So if I'm above this blue line up in here, I'm in the operate region. If I'm below the blue line, I'm in the non-operate or the restraint region. So let's talk about that actual fault. And that actual fault, I had differential current of 10 per unit at 0 degrees, right? Now, I haven't defined what restraint is. What restraint actually is restraint is the maximum of the two currents on the zone of protection. So if I've got 10 per unit, let's say instead of a 10 per unit fault, it's a 5 per unit fault. So my restraint's right here, right? And my differential, because it's a 5 per unit fault, is up here. So my actual point is right there. For that legitimate fault, I would operate. Now, let's talk about what would happen for that out-of-zone fault, right? Well, that out-of-zone fault that I mentioned, I said we had 10 per unit and 6 per unit. So that means, let me find my pen. There's my pen. So that means I've got a differential of 4, because 6 and 10 vectorially sum to 4. And my restraint is the maximum of those two quantities. So that means my restraint would be 10. So I would be somewhere out in here because we're off the graph now. But that's down here in the restraint region, right? So I would not operate. That's how we accommodate this with the slope differential characteristic. Now, we have to do this for any differential. But when we have a transformer, it becomes a little bit more complicated. So let's talk about why it's more complicated for a transformer. If you look at this typical transformer I have right here, I have a 13.8 kV transformer, or 138 to 13.8 kV transformer. And so if you look at where my CTs are sitting out here at, on outside of the actual windings, right? So right there's my CTs. And so that means that if I have 100 amps flowing out that 13.8 kV winding, I only have 10 amps flowing in to the 138 kV winding. So I have to accommodate that. Coming into the relay, I can't do that math in my head. 10, I'm not going to attempt to. But coming into the relay, I've got different quantity as well. So I've got to account for that in some way. And the way that I do that in a transformer is I do magnitude compensation. We'll talk about that a little bit later. There's another thing that I've got to account for in the fact that this current here, it's at 0 degrees. This one over here, where my CT is at, it's not at 180 degrees. It's probably at minus 30 degrees, right? So the X winding is lagging the H winding by 30 degrees. So instead of the current being presented to the relay being at 180, it's probably at minus 210 because of that 30-degree phase shift. And because of that, I've got to take care of that. And what I've got to take care of is phase compensation. I've got to take care of the fact that the angles on either side of the transformer are different. Also, if you look at this ground right here. So if I look at that ground, that's a ground source for any fault out in here. So if I had a B phase to ground fault out on my transmission system, let's say this is a generating station and I got a generator right here, that ground right there will pass zero sequence current to that fault. Now, because that delta to Y transition there, I won't see that zero sequence current on the generator side of this transformer. And that's going to cause me a problem unless I remove that in some way. So not only do I need to do phase compensation, I need to do zero sequence compensation as well. So I've got to do all these things with the transformer relay, protective relay. So here's the way that I can deal with that. Most of the settings that I need to deal with are found here in the actual winding setup. Now we'll talk about that in a little bit later, but I have to set my CTs, right? These particular settings are a UR relay. I think it's probably a T60. A little bit later, I'll show settings for an 8 series relay, an 845. But I have to set my CT ratios. Since it's a UR, I have to configure signal sources. And then down here, let me find my pen again. I'll keep losing my pen. There we go. So down here, this is where I set up my settings for my magnitude compensation, my phase compensation, and my zero sequence removal. So the settings on the UR are very much like settings for the 8 series. But basically, this first setting here, the MVA of the winding. The MVA of the winding, the relay will use that to calculate a reference winding for phase compensation, right? And that winding will be the reference for all of the other calculations. The ones that really start to matter are these settings right here, the winding voltage. Now, when it says the nominal phase-to-phase voltage of that winding. So for that 138 kV to 13 kV transformer, that's 138, 13.8. Now, the relay will use that nominal voltage. It will use that nominal voltage to calculate a magnitude compensation factor. So in this case, what that means is that magnitude compensation factor is going to be 10, right? So 138 divided by 13.8 kV, that's 10. So what that means is if I have that 10 amps flowing into the 138 kV winding, it's going to take that magnitude compensation factor and multiply it times that current. So now I have 100 amps, which is exactly what I have flowing out of the 13.8 kV winding. So the next setting I really want to talk about is this angle with respect to right here. So the angle with respect to is basically saying, what does this winding lag the first winding with? Most transformers that you will encounter in the wild that are delta to Y conversions or Y to delta conversions, it doesn't matter whether that's at a generating station or it's a step-down transformer at a distribution utility or a utility or a industrial facility, doesn't matter. Most of those transformers that you will encounter in the wild, the X winding lags the H winding by 30 degrees. If that's the case, if we make the H winding 1, we set the X winding to be minus 30. And we'll talk about how it does that a little bit later. Okay, let me find my pen again. There's my pen. And then this other setting right here, this within zone, basically that's saying, is there a ground source inside of that protective zone, inside of the CTs? Because our differential zone of protection is from the high side to the low side CTs. So in this case, it looks like my 13.8 kV side is wired in Y, so it has a ground source, which means it's solidly grounded inside of the zone of protection, so I set that to within zone. Okay, now the other settings that I need to build are the slope differential characteristic. Now there's a few settings that matter there. There is a minimum pickup, and so that's the point right here where the differential current has to be greater than that value before the thing ever operates. And then there is a breakpoint 1 and a breakpoint 2. Now breakpoint 1 is this point right here. Breakpoint 2 is this point right here. Now, below breakpoint 1, we use the low slope setting. And above breakpoint 2, we use the high slope setting. Now, what those slope settings basically say is how much of the differential do you need to have, of the restraint to operate. So below breakpoint 1, with these settings, if my differential is 25% of my restraint, I'd operate, right? So that means if I had 1 per unit of restraint, if my differential was 0.25 per unit, I'd operate. So in other words, if I had 2 currents, the compensated currents on either side of the transformer, one of them was 1 per unit, the other one was 0.75 per unit. The vector sum of those, assuming that the 0.75 is at 180 degrees to the other one, the vector sum of those would be 0.25. So my differential would be 0.25 and I'd operate. Now I'll talk about some guidelines for setting those a little bit later. But before we talk about some of those guidelines, let's talk about polarity. And let's open up another poll. And so the next question is, why does polarity matter? And the choices are, A, it properly determines direction relative to another quantity. That's wordy. You always have to have the dot away from the equipment. And C, it doesn't really matter. Polarity doesn't really matter. Oh, we can look, let me see if I can see the poll questions.
I expect 100% of people to get this right. And everybody
100%.
got it
100% of people said it properly determines the direction relative to another quantity. 100% got it right.
I'm so proud of y'all.
Are you sure that's the right answer, though, John?
Oh, somebody had to go miss it.
Yeah. Oh, here we go. We got some true believers here.
You're mean to me.
You should have closed it quicker, John. So go ahead and close the poll. And let me give you the answer, right? So let's see. Sharing.
Your screen's back up.
Okay, great. So CT connections, polarity. I'm fond of saying polarity doesn't really matter as long as it's right. right? Yeah, that's true. Polarity doesn't matter as long as it's right. And in reality, polarity is important because it does help us determine the direction relative to another quantity. But in a larger sense, doesn't really matter as long as it's right. And so what I mean by that is a lot of times people think that there's something magical about this little dot, on the CT. There's nothing magical about the little dot on the CT. All that little dot represents to us is which side of that CT is the H1 terminal and which side is the X1 terminal. So if we look at this dude right here, that's the H1 terminal, that's the X1 terminal. Now, typically, CTs are installed by the equipment manufacturer. The equipment manufacturers always puts the CT away from their equipment. They put the polarity dot away from their equipment. So this transformer, for example, you look at all these windings, the polarity dots are away from the equipment. But let's pretend, for example, for a moment that we got a breaker sitting out here, and it's sitting down here. Now, normally in a differential, you'd want to include as much equipment as you can into check here into the differential zone of protection. So that's where I draw that arrow down there. That's where you'd normally want your CT. So the breaker's in there. But let's imagine for just a moment that you wanted to use this set of CTs right here. Now, the equipment manufacturer, they would put this right here. They'd put the dot right here. So I've seen people wire things incorrectly because they always felt like they needed to wire up polarity on the relay to polarity on the CT. And in this case, because of the way we might do this, that'd be a problem, right? Because we got current flowing here. If that's flowing there, that means it's flowing into polarity on the relay, right? We got current flowing here. That means it's flowing out of the polarity on the relay here. Now, if we use this same set of CTs here, if we wired polarity here, it would come in here and current would be flowing into polarity. So if we were comparing this current with that current, we'd have a problem. So if that's the case, we need to wire it down here so that it would be flowing out of polarity or at 180 degrees. So polarity doesn't matter as long as it's right. What the 845, 745, T60, T35, most transformer relays are looking for is they're looking for a 180 degree difference in the currents. If you don't have a, phase compensation. Okay. Oh, there's a build. There we go. Okay. The other thing that I really haven't talked about that I should talk about is I've lost my pen again. Oh, there it is. Okay. The other thing that I really should talk about is transformer inrush. When we first energize a transformer, typically we will close one of the breakers. Typically, that is the higher voltage breaker. By closing the higher voltage breaker first and energizing the transformer in that way, there's less transformer inrush. And what transformer inrush basically is there is a large current that flows into the phases and basically flows out of the phases. So if we were looking at the other side of this transformer, the low side breaker is open. And this is what we would actually see on the relay, right? We see these on the relay, but we'd see nothing on the other side of the relay. And because of that, we would misoperate if we don't do something to block this, right? Now, these currents should vectorially sum to zero. We're not breaking Thevenin's node rule here or creating a perpetual motion machine. But since we're comparing currents on either side, we would misoperate. So we have to prevent that misoperation in some way. Now, the way that we typically do that is with harmonic restraint. And so basically what the relay does is it calculates, when we have these inrush events, it produces because of the saturation of the transformer itself that's being caused by these inrush events, we see a lot of second harmonic content. Okay, and that second harmonic content can be used to block the differential element when we energize the transformer. Now, the way that this was traditionally done back in the electromechanical relay days is they built a filter. Filter was tuned to 120 hertz. That filter basically provided opening torque to a coil. So it would keep the coil open. And as long as the opening torque was at least 20% of the differential torque that would try to close the coil, the relay stayed open. Right? This worked great for a long time. But what we see a lot of times now is with a modern transformer, we might see a completely different restraint scenario. So if we look at this actual event here that I've circled, the second harmonic content on A phase right here, that second harmonic content is just 9.9%. Second harmonic content on B phase is 13.6%. And the C phase is 38.5%. So an old electromechanical relay would misoperate on that because they were per phase. A and B phase would misoperate. Now, we have inside of most microprocessor-based relays, certainly the T60, T35, 745, as well as the 845, we have the ability to set an inhibit mode or harmonic restraint mode. And so our options on that harmonic restraint mode are we can set it per phase, like the electromechanical relays. We can set it on average, or we can set it at 2 out of 3. So the poll question that John's going to open now is, how should I set it?
Jerry, what happened to your question? Your answer of it depends. That's your favorite.
Oh, yeah. I didn't want to give anybody that option, right?
That's always your favorite option.
That is my favorite option. And honestly, that would have been the correct option here because there are some rare instances
I'm so disappointed in you today. It's just not like you.
Yeah, there are some rare instances where it depends would be the right answer, right? But in this case, that's your two choices. And so let's go ahead and close the poll, and I'll talk about what I think the correct answer is. So, yeah.
So 45.
Okay, so
39 said per phase.
Yep. So let's go back. So let's look at this data. If I did per phase, I energize this transformer, I'm not restraining on B and C phase. Or excuse me, I'm not restraining on A and B phase. I'm restraining on C phase. I'd trip, right? So per phase for this transformer wouldn't be the correct answer. And the reason it would be, I didn't mention this, but typically you would set the level of second harmonic at 20%, right? So the C phase is well above that 20%, but it's the only one that's above. So I'd trip this thing off if they did it per phase. The old electrical mechanical relays, they'd trip on this because they didn't really have a choice. They didn't even have a setting for the level of second harmonic. It was just hard set at 20%. And if I analyze the 2 out of 3, well, B and A phase are both less than 20%. So I wouldn't restrain there either. I'd misoperate when I try to energize the transformer. On this particular one, let's see, 13 plus 38 is 50, and another 9 puts me at about 60. Divide that by 3, and I'm at 20%. So I'd restrain here on average. And so I think the average is a much better setting for the level of second harmonic. Okay, let's jump in and talk about phase rotation now. So let's talk about what I expect to see for an ABC rotation. So here's my transformer. Got a delta on the H winding. Let's assume the H winding's on the left side, and my X winding's on the right side. And what do I expect to see for this ABC rotation? So that's what the voltages look like that I'm applying to the H winding, to that big A, that big B, and that big C. So those are at 120 degrees, which is what I expect, and I have ABC rotation. It's ABC rotation because if I imagine that vector diagram rotating counterclockwise, crossing the 0 axis would be A, B, and C. Now, if I look at little a, what do I expect to see on little a? Well, little a is a combination of A and C, right? So because of this dot right here, you know, what is on this winding right here is exactly in phase with what's on that winding right there. But the problem is what's on that winding right here is not actually A phase here. It's A minus what I've got on C here. So to figure out what I've got on A, I have to take the A here. So I take this A, right? And I'll take that C, and I'll superimpose C onto A, but it's minus C. So C's sitting right down here, and I get little a, right? Now, this is all at 1 per unit of magnitude. What I'm doing here is mainly talking about the angle. So that's how this 30-degree phase shift comes about, this 30 degrees phase shift across the transformer. Now, it's really important to notice that this 30-degree phase shift occurs because of the way the transformer is wired, right? So what we expect to see for this ABC rotation is this right here. So high side windings are at 0 degrees, low side windings are at minus 30 degrees. Because of the way our CTs are wired and the polarities facing, we should see the high side secondary currents at 0 degrees. And that's what we see right here. So red is the A phase. The red vectors are the A phase, the blue are the B phase, and the brown are C phase. So that's the high side. And we expect to see the low side, A phase, to be at minus 80, minus at 130. So that would be minus 210. That's where he's sitting. So that's what I expect to see under a normal typical transformer. Okay. What do I expect to see in secondary currents? This particular transformer is wonderful for secondary currents, right? Because, look at these secondary currents. I don't have to worry about magnitude compensation on this particular transformer. And that's why I say it's wonderful, because it's a 13.8 to 138 kV transformer. It means my magnitude compensation factor is 10. But look what I did. I did some I did some trickery around my CTs. I made my high side CTs 200 to 5, made my low side CTs 2000 to 5. So I didn't have to do that magnitude compensation in my head. So what that means is if I've got 100 amps flowing into the transformer at 0 degrees on the high side, I got 1,000 amps flowing out of the transformer because of the transformation ratio. But because of my CT ratios there, I've got 2.5 amps flowing into the relay from the CT on the high side and 2.5 amps flowing into the relay on the low side. Now, what that looks like is 0 degrees on the A phase high side and minus 210 on the low side. Now, what the relay actually does, we can think of this in a couple of different ways. And I think I'm getting ahead of my poll questions. I put my poll question in the wrong place. Let's go ahead and do this poll question. And let's see what you guys think here. And I think this is the one that Mike sent me an email, said that my poll question, he said I had too many words, which I don't mean if that was I was wordy or what. But anyway, the poll question is, transformer phase compensation in the relay is performed by A, magically shifting the currents, right, by whatever angle we need to, or B, figuring out how the transformer is wired based on the angle with respect to setting and calculating a compensation matrix using all the currents that are wired to do phase compensation, or C, it depends, right? So
there you go. There's your depends again. That's always
yeah,
right.
There. We got 17% that believe in magic. That's great. That's dropping down to 14%. No, it comes back. We got 10% true believers, 15%, 21% true believers, critical thinkers that think it always depends. As an engineer, anytime you see a multiple choice question, one of your choices is it depends, it is always going to be that choice, right? And in this case, I would say, you want to go ahead and close the poll question, John? The reason it depends is it just depends on what reality you want to live in, right? If you want to live in the magical universe reality, then you can believe that it just magically shifts those currents based on the angle with respect to setting. If you want to live in a mathematical universe, or if you happen to be a guy that tests the relay, you need to live in the actual universe, which is how this is actually done. And what we actually do inside the relay algorithm is based on that angle with respect to setting, is we calculate a compensation matrix. And that compensation matrix takes a combination of the currents that are wired to the relay and uses that combination of the currents to compensate. So, for example, the A that I show, I'm a pen, the A that I show right here is the compensated A. So what that looks like is I'm taking the actual wired A and the wired B, and I'm dividing them by the 1 over the square root of 3, and then I'm going to take those values and apply those to get my actual compensated A, right? And so that's how I actually compensate this. Now, the way that we used to take care of compensation back in the electromechanical relay days is we would wire the Y winding CTs in delta, the delta winding CTs in Y. We don't have to do that anymore. We can let the relay take care of compensation with the setting, or with the settings. So here are those same settings that I mentioned earlier in the 8 series versus the UR that I talked about earlier. The main thing here is that we're going to set this at minus 30 degree lag, and that's the angle with respect to. Okay, differential 8 series, same way. So let's jump through some of this because I'm running out of time. And let's look at how this actually works. So if we actually look at how this works, let's take those same currents that I talked about earlier, 2.5 at minus 210, right? And 2.5 at minus 330. So where's my, so it's this current right here, right? So this is where I'm compensating on, is these. So it's A minus B, right? So if I take 2.5 at minus 210 minus 2.5 at minus 330, that equals, if you can do this vector math in your head, 2.5 at minus 180. If you don't believe me, look at it. Here's minus 210, right? So let's see, that's minus 210 minus 330. And if we subtract 330, 330 would be sitting like right here, but we got a minus in front of it right there. So 330 would actually be sitting right there. So there is my 2.5 at minus 180. So that's how a combination of A and B phases can accommodate that phase shift. Get that back to minus 180. So then when I do my differential calculation and take my H winding current, that's 2.5 at 0 degrees, plus that 2.5 at 180 degrees, those vectorially sum to 0. If I wanted to figure out where I would operate, I could operate when, if I got this 0 differential point, if my slope's 25%, I'd operate when I dropped to 75% of my original value. Okay. So with that said, I am almost out of time. One of the things that I mentioned earlier was that it matters if you're a tester also. And the reason it matters if you're a tester is what happens if I inject a single phase quantity. Well, if I inject a single phase quantity, I don't have a B phase to actually compensate my A phase with in the calculations. So I get a very different value. So for testing purposes, it makes life a lot easier if you test injecting 3-phase quantities. So with that said, John, have we got any questions? Let's see if I can see your questions. You want to remind everybody how you ask questions, John?
They should be able to ask questions with the chat box. And right now we have no questions. You did such a good job, they have nothing to ask.
Yeah.
Or
we still have people here, right?
Yeah, I'm going to launch the last question.
Okay.
Which is, would you like someone from Levine Electronics Electric to contact you?
Oh,
I took away the question of you.
Yeah. Yeah, so Ed Robinson asked, he didn't have a question. He had a comment. So it looks like I misspelled poll. Probably not the first misspelling I've made, even in that one. How does one obtain?
There's questions.
Go ahead, John. I'll quit talking.
Can you see the questions?
I can. How does one obtain the slopes and the breakpoints? It's a good question. I ran out of time. John yells at me when I go over time, so when I run out, that's why I jump through all those slides, right? I'm really scared of John yelling at me.
You got 5 minutes to go back to one of them.
Yeah. Let's see. How does one, oh, I could have sworn that was in this presentation.
This is where, guys, just so you know, this is all not, it's not all science. There's an art to some of this.
Here we go. Here we go. So, if you're doing this, you want to set, let me find my pen. I've got your window, John, over my little icon for my pen. So let me get back here. So what you want to do is you want to set breakpoint 1. You want to set that low slope region to take care of CT inaccuracies in the steady state, right? What that means is under sort of normal conditions. You want to set that upper region to take care of CT inaccuracies when you have a real heavy through fault, where you can have heavy CT saturation. So for that reason, you want to set your lower break point to be the point where you are within safe limits of the CT operating. So in other words, you're not going to saturate. Not going to saturate for a fully offset waveform. If you do that calculation, that's going to depend on the size of your CTs, your fault current, the accuracy class of your CTs. That quantity may be anywhere from 4 to 2. As I said earlier, challenge on differential is not getting the thing to operate for a true differential. The challenge is to keep it from operating for a legitimate fault. So for that reason, I like to set things more conservative. I'll set that lower break point at 2. And typically, my recommendations are to set that at that lower break point at 2, regardless, if you've done the calculations or not. Now, the upper break point should be the point, the minimum current where you could get spurious differential because of CT saturation. Now, what I've seen people do is I've seen people calculate that. I've seen them calculate quantities for that. And if you're in a utility situation, you might have C800s and 3,000 or 4,000 or 5,005 CTs. And when you do that calculation, you have a quantity, a upper break point of like 15. That's not a good upper break point. I like to be more conservative, set the thing so I am less likely to misoperate. I'll set that down around 4. Sometimes I'll set it just above the lower break point, but usually my recommendation is set that around 4 per unit. Now, the real question you ask was, what should you set the slopes? Now, again, this is not going to be a scientific discussion, especially at the lower slope. The reason it's not going to be at a scientific discussion is that we have to make some guesses, some calls, right? So the first thing is we want to set that lower slope so that we accommodate error in the steady state. Now, the first thing that we can have error from is we can have error because if we're in the linear portion of the CT saturation curve, we can have 10% error. So I never want to set that below 10%. On top of that, I could have some error because I've got some remnants stored inside of my CT, right? So it may have had some remaining magnetism in that. Because of that, I'd add another 10% to that. So now I'm at 20% before I set my slope, minimum slope. That's for most differentials. That's for differentials on transform or stators, motors, or generators, buses, things of that nature. I could feel comfortable setting that as low as 20%. Transformers are a different thing because I've also got to accommodate some error associated with the transformer itself, right? I'll have no load losses in that transformer. Those no load losses can account for some error. I might have set the transformer for the nominal tap, but I might have it at a higher or lower tap if it's got a tap changer than the nominal tap. And unless I'm going to change my settings every time I change the tap, that's going to cause me problems. So typically on a transformer, that lower slope, I would say set that for 30% or 35%. Upper slope. The upper slope is where we could have a lot of CT saturation. Now, what we could do, one of the things we could do is we could model our CTs. We could use the PSRC tool that models CTs, and we could say, okay, this set of CTs is going to perform perfectly. So that looks like 10,000 amps, whatever it looks like. And then we could model performance and say, okay, this CT saturates. It looks like, 2,000 amps. That means I need a slope of 80%. That's one way you could do that. I would recommend that nearly everybody sets this by a rule of thumb. For that upper slope, that is not a light fault once you get up, past that upper break point. That's not something that is, if you're into that region, that's not a light fault, if it's a legitimate fault. So for that reason, you can set that upper slope extremely high. So it should be set to somewhere around 80% in transformers. With other differentials, stator differentials, you can set that down to around 60%. Minimum
Gary,
pickup.
You got two other questions I want to address. They're to get
Okay,
time.
yeah. Well, I didn't get through minimum pickup. You just have to yell at me, John, for going over time. Minimum pickup, I would never set that less than 10%. And the reason for that is because of that CT inaccuracy. And you can be more conservative than that if you go to a higher quantity like 20% or 30%. Okay. Let's find the rest of my questions. So,
Customer had an issue where he tripped on 80 differential when he started a large medium voltage motor.
okay. Start up a large medium voltage motor on the medium voltage bus. Then we trip the 87T. So if you trip the 87 transformer differential for the start of a motor, so that I would have to look at the oscillography for that to make a definitive statement. But what that sounds like you did was you had some CT saturation on one of the set of CTs, probably the lower voltage CTs on the transformer. So in that case, there are a couple of things that you could have. This is assuming that the transformer relay was wired correctly, right? That also can cause a problem, but let's assume the transformer relay is wired correctly. Then it is CT saturation, then what would be the issue there would be either the lower breakpoint setting or the lower slope setting, right? And again, a lot of times it's possible that you had a wiring issue that the relay wasn't wired correctly, or it's even possible that the relay wasn't set correctly. There are other relay manufacturers that don't use this -30 for angle with respect to. So I can remember back in the day, way back before I joined GE, when I worked for a utility, and I was using another manufacturer's relay, and I worked in TVA Hydro. And so basically it had this really cryptic code that you had to put in to tell it what the angle relationship was. It was either DABY or BADY, and I could never get that right? It was a lot worse than just -30. So they would start a motor, and they would say, hey, we picked up a little load here at the plant, and we tripped the transformer differential. And I'd say, okay, change it from DABY to BADY. So it could be any number of things from a CT saturation issue that could be addressed with settings, probably, to a settings issue with compensation or wiring. I couldn't say for sure until I could say for sure if I saw oscillography, but not without that.
That was great. We don't have any more questions, so I really appreciate your time today in presenting this to us. Tomorrow we have our own Michael McClellan doing the presentation on 8 ways to save space in a engineering room. Should be interesting. I'm looking forward to hearing what he has to say. So thanks everybody for attending, and be safe out there.
Thank you, John.
You're welcome, Terry. Thank you.